Okay.
So good afternoon, everyone. So in this presentation, I will talk about a study we did where we analyzed disfluency patterns at different levels of the language production system. Okay, I cannot. Yeah. So first of all, what we call disfluencies are all the phenomena that interrupt the flow of speech but do not add propositional contents. And even though these phenomena are really frequent, for now, no psycholinguistic models explain why they occur or take them into account. That's why in the current study, we first tested which disfluencies occur depending on lexical selection difficulty, grammatical selection difficulty, or conceptual formulation difficulty. And we also tested whether, by contrast, we could predict the difficulty, so lexical, grammatical, or conceptual, based on the pattern of disfluency associated with it using multivariate pattern analysis. And to do so, we use network tasks that are commonly used to investigate connected speech production. So here we can see an example of a network from the first experiment where we manipulated lexical selection and grammatical selection. So first of all, because we did this study among Dutch speakers and because Dutch is marked for gender, in each network, there were 4 pictures with a neuter gender and 4 pictures with a common gender. And to manipulate the lexical selection, we used name agreements, so the number of different names speakers can use to refer to an object. So in each network, there were 4 pictures with the low name agreement. So for example, in English, we can say boat or sheep or rabbit, bunny, and 4 pictures with a high name agreement, like leaf, for example. But except from these manipulations, all the pictures were matched for their lexical frequency, age of acquisition, or their length. In the second experiment, to create difficulties at the conceptual level, we used blurriness. So in each network, there were 4 pictures that were blurred and 4 pictures that were control pictures, and this was counterbalanced across participants. But all the pictures were matched for their name agreement, age of acquisition, lexical frequency, and visual complexity. So that's the thing with network tasks, is that we can specifically manipulate one level while holding other characteristics quite constant. And to choose for this experiment, to choose the best threshold of blurriness, we first use a naming experiment with these different thresholds, and we chose the one that induced longer reaction times compared to control pictures, but not more errors or do not know answers. So that's why we chose this threshold. So more concretely, during each experiment, participants were sitting in front of a computer. There was first a fixation cross on the screen, then a network appeared for 2 seconds, and then a dot appeared on one of the pictures and started moving through the network. And the participant had to describe the path of this dot while staying synchronized with it and while building full sentences. So for each experiment, we recruited 20 Dutch participants, and they underwent 20 networks. So we transcribed everything and we annotated all disfluencies, but we only analyzed the ones that were related to pictures name, not to path, for example. And we took into account self-corrections, filled pauses, silent pauses, prolongations, and repetitions. So like I said, in the first experiment, we manipulated lexical selection and grammatical selection. So we tested with linear mixed effect models if low name agreement pictures induced more disfluencies, and if the neuter gender, that is less common, was also more difficult and induced more disfluencies. And in the second experiment, we used these linear mixed effect models to test if blurred pictures induced more disfluencies. And in each experiment, we conducted MVPA, so multivariate pattern analysis, to see if we could predict name agreements gender, or blurriness based on disfluency patterns. So I will just maybe say a few words about multivariate pattern analysis. Most of the time, when we conduct analysis, like dynamics defect models, we use, we're in multivariate and univariate analysis, so we focus on one dimension, let's say here are self-corrections, and we see if the two conditions or the two group of participants are different. And then we focus on the second dimension, and we do the same thing. But with multivariate analysis, we will take into account all dimensions together, and we will try to find the best angle that could distinguish participants or conditions. So here we tested if a classifier was able to learn and then predict the type of item based on differences that are associated with it. So in the first experiment, 16% of pictures induced at least one disfluency. When we analyze all phenomena together, here we can see that low name agreement pictures induced more disfluencies than high name agreement picture. And contrary to what we expected, the common gender, so the blue bar, induced more differences than the neuter gender. And there was an interaction, common gender by name agreements. When we analyze each phenomenon individually, we can see that low name agreement pictures were associated with self-corrections, silent pauses, and failed pauses, and the common gender was associated with more prolongations. Here we can see the results from the classification. So the classifier was able to predict above chance both name agreement and gender. So if we focus on name agreement first, we can see that each disfluency significantly contributed to the classification, which means that the classifier found information in each of these features, and that these features were consistent across participants. While for the grammatical gender, only prolongations were found consistent across participants. So this reinforces findings from the dynamics defect models. So to sum up these first experiments, we first showed that lexical selection difficulty induces self-corrections, silent pauses, and failed pauses, which is replication from a previous study from Hartsuiker and Notebaert. And contrary to what we expected, they were more prolongations before common gender, but neuter gender didn't induce differences. So we think that this can be due to the phonological form of this determiner, that is de in Dutch. So we can imagine that if the participants have difficulty to name a picture for some reason, it will be easier to prolongate the before naming the picture. And MVPA reinforced these findings because it showed that disfluency patterns are informative about the linguistic difficulty, because a classifier was able to learn and predict both name agreement and gender. And it also showed that some features were stable across participants. So during the second experiments, where we manipulated blurriness, 26% of pictures induced at least one disfluency. But contrary to what we expected, blurred pictures didn't induce more disfluencies than control pictures. So not when we analyze all phenomena together, and not when we focus on each phenomenon individually. So yeah, this is totally unexpected. Regarding the classifications, it was above chance level, even though it was not really high. But no features were significant at the group level, and we can see these big error bars. So what does it mean? It means that within each participant, the classifier was able to learn and predict if she or he was able to name a blurred or control pictures, but this pattern was not consistent from one participant to another. So there were no features that were stable at the group level. So in this second experiment, we didn't find any effects of blurriness on disfluency prediction. There is, however, probably one limitation in this experiment compared to the first one, and it's the fact that here the manipulation was quite obvious. So probably that it had an influence on the whole task, because when participants saw the networks, they could see that some pictures were kind of hard to name, and probably that it had an influence on the whole task, not only on these specific pictures. But still, multivariate pattern analysis show that there is probably an effect of blurriness on disfluency patterns, but that this pattern is not consistent across participants. That basically a conceptual difficulty manifests itself differently from one participant to another. So to sum up the whole conclusion, we first show that determinant selection led to a different pattern of disfluency than content word selection. So in that sense, it reinforces the conclusions from Hartsuiker and Notebaert, who said that that difficulties at distinct stages of language production elicit different types of disfluency. So we didn't find any effects of grammatical selection. So probably that grammatical selection is not difficult because it occurs after the lexical selection. But still, we have to find a better way to be able to use network tasks when we want to manipulate the visual identification of some items, because we think that in this specific situation, there is an influence of the visual attention and visual control that interfere with the language production. And in this study, MVPA provided complementary findings, either by reinforcing findings from linear mixed effect models and showing some consistency across participants, like in experiment 1, or by showing that conceptual difficulty manifests itself differently from one participant to another. And this is calling for further research on the underlying factors that could shape these inter-individual differences. Thank you.